Hello, everyone. I'm Charlie. I'm a final year student at the University of Liverpool, supervised by the battalion Catarina. My project is about extracting information about PyPy co-crystal um, from the Cambridge structure database and trying to apply the machine learning to facilitate the discovery of new type of co-crystal. In this presentation, I will first mention the definition of PyPy crystals and then describe the history of the study in terms of aims, challenges, and basic process of co-crystal prediction. Then I will introduce the concept of pure learning and describe how we put this theory into practice. Well, co-crystal play an important role in the pharmaceutical industry by perceiving the pharmacological properties of API while improving the physical chemical properties of the drug. So what is a co-crystal? In simple terms, a co-crystal is a combination of two or more different molecules such as maybe in a particular composition. So co-crystal has important places in the pharmaceutical field. For example, during a pandemic, the NHS recommended that the COVID-19 self-isolation patient to be given paracetamol during with high temperatures. However, the medical properties of the paracetamol impure or poor, which means that it's not easy to make tablets. When co-crystallizing with other molecules such as theophylline, it's possible to achieve an easy tablet form. So co-crystal not only valuable for in the pharmaceutical field, but we also interested in the specific structure such as pi co-crystals. Previously, we had defined a crystal consisting two or more molecules which can be connected with different types of non-covalent bonding, such as the hydrogen bonding or pi-pi stacking. In this study, we'll focus on the pi-pi stacking. In general, the process as a common co-crystal molecule building block for generating pi-pi bonds. For example, here methylene is the simplest process. So what is the purpose of our research? Our aim are designing a binary classification model that given two different molecules, and we predict whether a combination of these two molecules can synthesize a new pi-pi co-crystal. However, there's still some challenges in the current field of co-crystal prediction. Firstly, it's a huge imbalance between the positive and negative in addition to the fact that the field co-crystal synthesis is unreliable as we use as negative examples. Let's first understand the reason for the current imbalance in the data. It's caused by the fact that almost all the literature provides only successful synthesis experiment and not field one, thus leading that series imbalance. In our research, we searched the Cambridge structure database for nearly 1,800 positive samples. However, the lab only provides us 11 bias negative samples with variant and it's very huge data imbalance to read. So it's difficult to accomplish the purpose using traditional binary classification. So then let's talk about the negative. Negative samples in co-crystal synthesis experiment can be unreliable. So because we can confirm successful co-crystal synthesis by some instrumentation, however, for field ones, we often need to rule out all possibilities. In co-crystallization experiments, the negative samples are unreliable because the result of experiment often depends on the experimenter's method, solubility, and maybe temperature or the time. So, for example, in 2013, Wood Group labeled this combination as negative. However, the Koulas group found that these combinations could form a new co-crystal. Once we understood the current challenges, let me introduce a basic process of co-crystal prediction. First, we need to extract and train our current data. Then select a suitable machine learning algorithm for classification. In addition, we need to evaluate and do some hyperparameter tuning to select the best model we have. And finally, we send to the lab to do some experiments. The data determine the upper limit of the algorithm. So let's first understand the purpose of data extraction. In this work, we used three different data sources. As you can see that the first we use is a Cambridge Structured Database CSD, which was used to track non-passes co-crystal. The second is the 16.5. We can simply understand to be a molecule database. The third is the 11 field experiment we can have. We first select about 3,000 co-crystal deposits in the CSD, then using the Link 16.5 database. Here we select 210 molecules to extract all available combinations. The purpose of generating these combinations was to generate the unlabeled dataset in which some samples are positive and some samples are negative. You can see that we use the Cartesian product here. So our aim in generating the unlabeled samples is find some hidden positive in the unlabeled sample. After extract the data, we need to represent these molecule combinations and to the features, and we use it a Mordred descriptor to pass these molecule combinations. Mordred is a library to extracting molecules by calculating some maybe physical properties. For example, for the positive data, the blue boxes here represent the feature vectors. Once the feature has been represented, we then need to perform feature extraction and data normalization before feeding the data into the machine learning model. So next, let's talk about the model workflow we try. At the beginning of the project, we use the data processing methods such as oversampling and undersampling, also use the dbScan. For the unbalanced data set, it's a very common approaches. And for the next workflow, we use the one-class classification, and thirdly, we use the pure learning. It's called positive and unlabeled. So the first workflow uses a dbScan to remove alters from the positive data set. Then the number of difference between the positive and negative was balanced by the random undersampling method, and oversampling method just be used as mode algorithm. However, the use of data processing method is to construct the traditional binary classification. That model is problematic due to the extreme imbalance between the positive and negative, and the fact that we use for the field experiment the data were unreliable, and it's bias sampling, so it's not effective if you use this method. Okay, so let's talk about one-class classification. It's using only positive data that can provide some problems such as unreliability of negative. However, a co-crystal prediction by the one-class classification have been used. So by the Katarina. So we would like to take another view to this problem. So we try to use the pure learning to solve this problem. So the method we decided to use is PU, and PU learning only use the positive data and unlabeled data. Here we use a very simple example to describe the basic concept of PU learning. For traditional binary classification, a specific dictation boundary can be generated if we use the positive set and negative set, but we don't have negative set, so traditional method is not useful here. So next graph is we use the one class classification. You can see it only use the positive data here. So another decision boundary can be generated. It's reasonable. It seems reasonable. And if we use the pure learning, in this case, we have the same reasonable decision boundary. So we can use this method to avoid the problem that manual labeling is unreliable for field co-crystal synthesis in experiments. Okay, next we give the definition of pure learning. So given a set of examples of particular class positive P and a set of unlabeled sample U, which contains both class P and negative instance. The goal is to build a binary classification to classify the test T into two classes, positive and negative. So where the test T can be unlabeled. So let's talk about the label mechanism of this, of PU learning. So in the key point in the PU problem, so if a sample is selected to be labeled with as equal to 1, then it belongs to the positive set. Otherwise, the sample label is not unknown, so it belongs to the unlabeled set. Here we use the graph to describe this experiment in the crystal prediction problem, maybe in the lab. So we first check the unlabeled data, unlabeled combination, and if we're not sure the result, we put them back to the unlabeled data. And if we have some result, it means that we have a positive result. So we put the unlabeled set to the positive set. This is the basic process. And once we have introduced the unlabeled samples, um, we must make some assumption about labeling mechanism, which we will refer as a selected completely at random, SKAR. In this assumption, labeled examples are selected completely at random. It's independent from their attributes. So you can see that this graph, the blue curve, is a real positive distribution, but we don't know. But we only have the green curve here. So that means the labeled positive. So we have an important theory which can transform the PU learning problem into a traditional dynamic classification problem. Please note that the following equation, where the rightmost conditional probability represents the probability of a positive occurrence given the feature X and under the binary classification. And when we compare the probability of positive means that y equal to 1 giving X, and y equal to 0 giving X. We can know that this is the model prediction results. And there is a similar to the PU part here. So so it represents the probability of labeled samples occurrence given the feature X under the PU learning. And please note that the middle one means that um, the proportion of the labeled data out of the total positive data, but we don't know the real ratio it is, but we need to make some assumptions, make a very low value here. And if we're using that equation, we can terminate into the some prediction threshold. For example, in the traditional binary classification, we have a traditional threshold, the tau. We can know that the tau multiply the C. The C means that this proportion here. And we can transform to the traditional to the PU part. So the PU threshold is equal to the normally it's 0.5 multiplied C because in the traditional it's the threshold is normally to the half. And we try to use this method to get some reliable negative. We will see later. And then let's understand the specific algorithm of PU learning. So there are several basic approaches to the PU learning. We first use the two-step PU learning. In the first step, we obtain some reliable negative samples in the unlabeled data. And the second step, we use the positive and the reliable negative to train a traditional, or maybe you can call it supervised learning. So the key point here in the step 1, you can see that this is the PU threshold. So we select the least likely positive samples as a reliable negative. Okay, so what method do we use to get reliable negative positives in unlabeled samples? Here we use the SPI technique. Here, the SPI technique is used in the first step. Let's talk about the SPI first. So we first do some positive samples of SPI are randomly selected from the positive P. And at this point, we call the U prime is union of SPI and unlabeled data. And the P prime is a positive data minus SPI. So we remove the SPI from positive and call the P prime. And we treat this, we we do some classification using the random forest with P prime as positive samples and U prime as negative 0. And thirdly, a subset of unlabeled samples with prediction probability less than a threshold is selected as the reliable negative Rn. So this is the first step of pure learning, and we obtain the reliable negative here. And next, we do the traditional binary classification to use the positive P and the reliable negative. Okay, so how do we evaluate the model we get through the pure learning? For traditional binary classification, the F1 sources is important metric. The F1 sources is dependent on the position and the recall we define here, and we also have a confusion matrix to give you the tip. However, have you noticed that the pure learning problem does not apply to the F1 sources? Because due to the lack of actual negative, we don't know the active negative. So it's not possible to calculate the precision that the F1 source cannot be calculated either. So in general, for the co-crystal prediction problem, we can only use the recall to evaluate the model. However, the high recall rate is just the one thing. We want the algorithm to have some ability to find some hidden positive in the unlabeled set. So let's first look at the recall result first here. So in the first finger, we use the one class classification. So it's used the isolation forest. The green zone here represents the standard deviation, and you can see that the learning curve of this model is not very stable, but finally it will get some higher point relatively. And if we use the pure learning, it's much stable than the isolation forest. And if we just use the traditional binary classification, please note that here we mentioned the traditional. It means that we treat all the positive to the 1 and treat all the unlabeled to the 0. Maybe you can refer to the first step in one-step pure learning. It's okay. So you can see that result is both okay, but this method can help us to find some potential high hidden positive in the unlabeled set. So let's see another experiment we do. So an experiment will carry out, we simulate the process of discovering new co-crystals by hiding some of the positive data in the unlabeled data. In this research, we trained 3 different types of classifier using all positive samples with level 1 and level 0 to the unlabeled. Before that, we modified 95% of positive data to the unlabeled. That means we hidden positive samples. We hope to use this method to compare the ability of different algorithms to find potential positive in the unlabeled data. So in order to represent the number, we use this finger. First, the x-axis represents the number of unlabeled samples that we select as having the highest prediction probability of the classifier. And the y-axis represents the percentage of our hidden positive found in these unlabeled samples that we select as the highest prediction probability. For example, we select 1,000 unlabeled samples with highest prediction probability. For traditional binary classifying or the one-step pure learning, nearly 80% of unlabeled data are founded. That is the hidden positive. I can think that the pure-based learning algorithm can effectively find our hidden positive samples while the one-class classification is both okay. For the traditional binary classification, since most of prediction probability are around 0.1, the proportion of hidden positive sample obtained by this algorithm is significantly reduced after we select 1,000 unlabeled samples. We also did an additional validation set in which we select positive and negative samples that are not learned by this model. So we rank the predicted probability and find that positive data were largely at the top of the list. Since we use the real data, this means that our model works well or it works. And finally, let's summarize this. So data processing methods do not handle this problem well, and the negative data, because of negative data, is unreliable. And the pure learning algorithm has a strong ability to find potential positive samples, and it just take a different view of problem than the one class classification. Okay, so finally, thanks to the Vitaly and Katerina also for the help of this study. And thanks to the Olga for her valuable comment on the detailed proposal. Thank you very much.